Assalamu alaikum warahmatullahi wabarakatuh. We are just moving to the part there we can solve a differential equation of any type, and that's where you're going to use the power series method. Till now we have done first order linear differential equation, first order differential equation in any form. We have discussed also the equations, second order differential equation with constant coefficients and second order differential equation with variable coefficient. Special form was Cauchy-Euler equation. We have discussed the method for finding the solution of the higher differential equation with the help of reduction of order. Then we having undetermined coefficient and variation of parameter. Now move on to a method which can be applied to a any differential equation, and mostly we solve with this one, first order, second order differential equation, not the third order. As I say, in nature we are having most of the problems in second order differential equation. There are very few problems in the fourth order differential equation. We focus on second order differential equation, and this method can be applied, as you have seen that variable coefficient we said, but we haven't taken very special form of the Cauchy-Euler equation. If you remember it, in Cauchy-Euler equation we are having this, that we are having a2, then we are having x square y double dash plus a1 x y dash plus a0 y equal to 0. This was our Cauchy-Euler equation. There being the second derivative being multiplied by x square, first derivative multiplied by x, this very special form. If I have the equation like this one, a2 y plus a1 x square y dash plus a 0 y equal to 0, we can't apply this Cauchy-Euler equation method for solving this problem, because this is not in the form, the standard form we are having for the Cauchy-Euler equation. For that one, we are having this method. This is our method for the power series. We can apply it by any type of the differential equation. Constant coefficient, variable coefficient in any form, homogeneous equation, non-homogeneous equation. So it's a standard method for solving all type of problems. Here you are having the series, and we have the power series. I hope I'm just considering that you know the series, and so I don't need to revise all these things. We can have the series, power series about, we can expand any series about x equal to x0. Then we say our y is equal to Cn x minus x0 to power n, and here we expand it from n is from 0 to infinity summation form. When I expand this one, we can have here y equal to C0 plus C1 x minus x1 plus C2 x minus x1 whole square plus C3 x minus x1 whole cube, and so on. This is my expansion of this y in terms of this series. Now here we say this function y is analytic about the point x equal to x0. I am just changing it to 0 instead of 1. So x equal to x0, this is analytic. Analytic means it is differentiable, and when differentiable obviously is continuous. The continuous obviously is in the point is in the domain. The function is defined on that one. If the function is not defined at the point, we say this is not analytic. So this the function is analytic at the point x equal to x0. We can expand in terms of the series, and we use, for example, specially we use the series when we having the series is analytic about x equal to x0. We can write our series y equal to sigma n is from 0 to infinity Cn x to power n. So this analytic about x equal to 0, put here the value of x0 equal to 0, we can write like this. When I write the expansion of this one, I get here y equal to C0 plus C1x plus C2 x squared plus C3 x cubed, and so on. Now interesting is that as we were doing in case of the Cauchy-Euler equation, or before we having using this with the constant coefficients, so we replace our equation, differential equation, because this contains the derivatives, and that means we need the derivatives. So here we can we can take the derivative or integration of this one as it is analytic term by term. If I want to differentiate it, I want to find dy by dx. So my dy by dx is term-wise differentiation. Derivative of a constant is 0, and derivative x is 1. We get here c1 plus 2c2x plus 3c3x squared plus 1. We use here the formula. We say this formula d by dx is x to power n, a power rule, n x to power n minus 1. We're using this rule of the differentiation applied here. We get the first derivative, and mostly if we have a second order differential equation, we need a second derivative also. to replace that one, I just take the second derivative. I have second derivative d2y by dx square, and this is equal to, taking derivative of c1, that will be 0, and here we get here 2c2 plus 3 into 2c3 x plus, I just expand this one also here, 4c4. Here we can have this here, x to power 3 and so on. So here we get here 4 into 3 x to power 2 and so on. So this is my second derivative of this one. So we're having here y, we have y dash, y double dash. These are the terms we need to substitute in our differential equation. We'll try, if possible, to take the equation that the equation is analytic about x equal to 0. That means we can replace our y dash and y double dash with the help of the derivative of this one. We can write this one is also in the form of the expansion here, as we have here this one. We can write this one also. We can see this is from n is equal to 1. So we can write this is equal to sigma n is from 1 to infinity n x to power n minus 1. We take any value of n, we will get here. For example, I take n equal to 3. So n equal to 3 is 3 x to power 3 minus 1, that's equal to 3 c3. Here is cn and cn. So we have c3 x to power 2. So similarly, we can write the summation form of this series, and we can write this equal to, the sigma is n is from 2 to infinity, because we are having here the value of c0 is 0 and c1 is 0, because we differentiate this one, is a constant, becomes 0 is constant. No, it's starting from 2. And we are having here n minus 1. Here is n is 4 minus 1 to power 2. So I can write here n into n minus 1 x to power n minus 2. So we can take, for example, n equal to 4. When we take it is 4 into 3 x to power 4 minus 2. We get here this equation. Here is c4 also. This is missing here. This is c4. And we can get this equation. So in principle, we're having these formulas that we need to replace when function y is analytic at x equal to 0. Then we replace y is equal to sigma n is from 0 to infinity cn x to power n. Then we're having y dash, it's dy by dx is equal to sigma n is from 1 to infinity n cn x to power n minus 1. Y double dash is equal to sigma n is from 2 to infinity n into n minus 1 cn x to power n minus 2. You can understand from here also that we are having here the derivative of this one is n x to power n minus 1. Again, derivative of n minus 1 is n minus 1 x to power n minus 2. So these are the idea why this value is going to 0, why the summation is changing from 1 to infinity and 2 to infinity. This is very clear from this explanation to you. Again, I have this because this is an important point. You must understand that one, that we are having c0 is constant. We can differentiate this one. This becomes 0. Derivative of x is 1. Derivative of x square is 2x1. Derivative of x3 is 3 x to power 2, and derivative of x to power 4. I can write here one more term. This is c4 x to power 4 and plus so on. So derivative of x to power 4 is 4 c4 x to power 3. And then the second derivative, because c1 is constant, so becomes 0. Derivative of x is 1. Derivative of x square is 2x. Derivative of x3 is 3x square. And we have just combined this one because I have the value of y here. So I just try to find the value of y dash. This is because n is now from 1, not from 0, 1 to infinity. So we're having here n x to power n minus 1, 1 to infinity here. And it's changing from 2. So we get here 2 to infinity and n minus 1 x to power n minus 2. So this is the basic idea for the Fourier series, that for the power series we can apply for solving our problem. Now one more thing which we need, that when we can use the series, define the series when x equal to 0. So we are having the general form of our equation with the variable coefficient y double dash plus a1 of x y dash plus a0 of x y equal to 0. I say this is my standard equation. So I normalize my equation. Normalization means I make this coefficient 1. So I divide by a2 of x. We can have here, I say this is my equation 1. And I divide by a2 of x. I get here y double dash plus a1 of x over a2 of x y dash plus a0 of x over a1 of x y, and this is equal to 0. When I change this one, I say this is my y double dash plus p of x y dash plus q of x y equal to 0. What's my p of x? My p of x is equal to here a1 of x over a2 of x. And here is my q of x. My q of x is equal to a0 of x over a1 of x. When I want to define my series, so this is my number 2 solution, then we say this is the solution must be analytic about x equal to 0. This means it's defined, it's continuous, it's differentiable, and we can expand this one in terms of the series. Analytic means we can expand in terms of series, and then as we say we can differentiate it and also we can integrate it.